Good afternoon, and welcome to today's webinar featuring research and technology demonstrations sponsored by the International Space Station National Laboratory and launching on board SpaceX's 29th Commercial Resupply Services mission to the orbiting outpost. I'm Patrick O'Neill, Public Affairs and Outreach Lead for the ISS National Lab, but since it is also Halloween, figured I would double today as James Tiberius Kirk, Captain of the USS Enterprise. For those that are also interested, I do believe that it is stardate 10/14/28.88. So feel free to check me on that to ensure accuracy. Okay, today will be an opportunity for media and the public alike to learn about some of the projects that will be performed on the station in the coming weeks. Launch presently slated to take flight no earlier than 10:01 p.m. Eastern Time on Sunday, November 5th from Launch Complex 39A at NASA's Kennedy Space Center in Florida. Okay, so a little housekeeping up front for the attendees. Members of the media, should you wish to ask a question, please raise your hand in the Zoom and we will work to unmute you. For the general public, should you wish to ask a question for consideration, please use the hashtag ISS National Lab. Okay, before we get into the specific payloads on this mission, we are also joined by science leadership within the ISS National Lab and NASA's ISS program to provide remarks on this mission and the state of the orbiting laboratory. To kick things off, I would like to first introduce Michael Roberts, Chief Scientific Officer for the ISS National Lab. From there, we will hear from Meghan Everett, Deputy Program Scientist for the ISS program at Johnson Space Center in Houston. Dr. Roberts, the floor is yours.
Thank you, Tiberius. This is an honor to be introduced by the captain today. Welcome to everyone who's joining us on today's webinar. We're very excited here at the ISS National Laboratory. This will be the last Commercial Resupply Services mission to the International Space Station of the year, but we've had a very busy year. This will be the fourth launch in this calendar year, bringing more than 135 payloads to the International Space Station, which would be the highest number of payloads sponsored by the ISS National Lab in a single calendar year to date. As I hope everyone here knows, the ISS National Laboratory was created with the specific purpose to support increased access to low Earth orbit and space for the support of research, technology development, education outreach, and workforce development that benefits us here on Earth. So the ISS National Laboratory operates in parallel with our partners at NASA to continue to explore space and to support access to space for technology development and research that benefits us here on Earth. We have seen here at the ISS National Lab in this past year the continuing growth of the commercial sector and the engagement of multiple other U.S. government agencies in seeking access to space. And this particular mission is reflective of that in the diversity of payloads in the life and physical sciences. If you've had a chance to visit our website or you've received our most recent update on the CRS SpaceX 2029 launch. If you haven't, I encourage you to visit. It is very appropriate for today's theme of 31 October. Microbes, mucus, and brain organoids are just a few of the exciting payloads supporting science that are going to station on today's launch. Today, you'll have the chance to hear from some of the research teams that are operating these payloads, design these experiments, and are anxiously awaiting the launch of CRS-29. You'll be excited to hear a bit more about these projects, just as I am, and the impacts that they might have on the scientific community as a whole. With that, I'd like to kick it over to Dr. Meghan Everett, the Deputy Chief Scientist for NASA's International Space Station program, to talk a little bit more about the projects that are flying from NASA's side of the house. Meghan?
All right, thank you, Mike, for that great introduction. So similar to Mike, I am really excited to get to talk about some of the science that is flying up on SpaceX 29. So as Mike said, this is a really big science mission. We have nearly 1,600 kilograms of mass flying up on the vehicle. And on the NASA side of the house, this includes approximately 15 investigations that touch on areas of human health and performance, technology demonstrations, education outreach programs, fundamental science, and even Earth observations. So I would love to have 30 minutes and highlight all 15 of our different investigations, but I only get a couple. So I'm going to highlight some of the ones that really hit hard on NASA's mission to support some of the novel research that improves Earth-based capabilities through space innovations, and then some of the research that improves science capabilities on ISS for future exploration missions, supporting those programs to go beyond low Earth orbit. So the first two that I'm going to talk about are on the outside of the space station. And so the first one is called Illumity, and that is looking at optical communication to allow for lower power and smaller hardware to send data packages from the International Space Station all the way down to Earth. And this capability would tremendously enhance our science that we're doing on the space station, because we can get more data down to Earth faster, allowing the scientists to analyze their data faster and make quicker decisions on how to go forward with those next steps. The next one I'm going to talk about is called AWE, and this is an atmospheric waves experiment. So this is looking at atmospheric waves, which are just kind of, you can think of them as little pockets of energy going through the atmosphere. And they're very, very tiny in the lower atmosphere where they start. And then they grow as they go to the upper atmosphere, closer to ISS, where we can measure them. So this is a brand new capability to be able to measure these atmospheric waves. And we're hoping these atmospheric waves will tell us more about space weather. So we'll be able to look at winds that might impact satellites, or even tell us more about climate changes, which are very impactful for here on Earth. The next two investigations, I'm going to move you to the inside of the space station. So we'll do this work inside the International Space Station. And the first one is looking at, it's called Aquamembrane 3. And this is looking at aquaporin proteins, which are naturally occurring in living cells. And we're looking at the ability for these proteins to filter water. And we all know that clean water is a huge problem on Earth in poorer areas, or areas where we have military going in, or just extreme environments. So the ability to improve our water filtration capabilities could enhance not only astronauts' ability to reuse and recycle water, but also be a huge benefit to, again, those places in extreme environments here on Earth, or where we can improve the health of humans on Earth in those at-risk populations. And the last one I'm going to touch on is called cell gravasensing. And this is really exciting because it can be impactful for our astronauts on the space station who experience losses in muscle strength and bone health due to not having gravity on their bodies, as well as disuse-related diseases here on Earth. And so what this study is looking at is the ability for one single cell to respond to the sense of gravity pulling on that cell. And when the gravity pulls on that cell, the cell responds by releasing proteins or other molecules that would help promote muscle strength or promote bone health. And this ability to respond to gravity is really, really hard to measure. And so one of the things we're excited about being able to do this on the space station is we have these great microscopy capabilities where we can do imaging called confocal imaging, where we can actually look at molecules flowing in and out of the cells while they are positioned in microgravity on the space station. So this is brand new research, super novel capabilities, gold standard level research that we're doing on the space station that will hopefully give us great information on disease populations and improve our ability to maintain human presence in low Earth orbit and in exploration destinations outside of low Earth orbit. So with that, I'm going to pass it back to Patrick to carry on with the rest of the show.
Awesome. Well, thank you so much. Greatly appreciate both Dr. Roberts and Dr. Everett for joining us and providing your insights. Also great to hear about some of the NASA investigations that will be going up on this mission. But that said, now we are going to switch gears a little bit and bring in some of the research teams that are sponsored by the ISS National Lab on this mission. Again, as a reminder for media that are joining us in the Zoom, if you would like to ask a question, please raise your hand and we will unmute your line. For those that are joining via the webcast, please send your question using the hashtag ISS National Lab. Okay, first and foremost, I would like to introduce Dr. Emily Dresser from the University of California in Santa Barbara. Dr. Dresser and her team are leading the gaucho lung experiment, which I imagine has something to do with the human lung. So Dr. Dresser, good morning to you on the West Coast. And
good morning.
Please tell us a little bit more about your project.
Happy to tell you more. Thank you, Patrick, for the introduction. So our team is interested in what is called the respiratory distress syndrome. And so what this is a respiratory deficiency or difficulty in breathing, and that can be caused by different things. It can be due to an infection, or it can be due to premature birth, right? And that's going to be the case for about 1 in 10 premature babies. So what we're interested in is optimizing the treatment that is provided to those patients. So the treatment as it is right now is drugs are loaded into a fluid, and then this fluid is injected directly into the patient's trachea, and it's going to make the drug and the liquid are going to make their way into the lungs up to the very small nooks and crevices inside the lungs, and then facilitate the breathing once they get there. This treatment works great for infants. It doesn't work as well for adults, and so we've been trying, and other teams have been trying to understand why. And so you have differences between the lungs of an infant and the lungs of an adult. Size is the first effect that you can think about, so you can think directly about the effects of gravity there. The amount of branching is also going to be different in our lungs versus the lungs of a baby. And then the last effect, which has really not been studied that much so far, is the effect of mucus. Adults have a lot more mucus, especially when they suffer from an infection, than infants do. And so how does the mucus in our respiratory system affect the transport of those drugs and those plugs of fluid? That's really the question we're trying to answer. And we're engineers, right? We're fluid mechanicians. So that's what we're going to focus on, right? And then we're going to try and build this fundamental knowledge, build this understanding so that, the biomedical side of develop and their development can pick that up and really develop improved treatment. So what are we doing and why do we need the ISS? So as I was telling you, we're engineers. So we're looking at flow in tubes, not directly, in the respiratory system of a human or a mouse. We're simply going to use those tubes and we're going to look at the transport of liquid. Our tubes are gel coated. And if we run experiments in the lab, it's really hard to differentiate the effect of gravity, surface tension, or capillary effects, and the role of the mucus, right? All of those things are going to be combined, and then you can even add to that inertia if your tubes are really big or if you're pushing the plug really fast. So everything is mixed together. As soon as we want to separate those things, what we have access to on Earth is the size of the tube. If we use small tubes, we have capillary effects dominant. If we use large tube, we have inertia and gravity dominating the flow. But we can't use large tube to probe those capillary effects without dealing with gravity. So that's why we're going to space, right? We're trying to separate those different effects so we can understand the role of capillary effects, the role of gravity, the role of inertia, and then how the mucus is modifying all of those, or is affecting all of those effects. So we've developed a really strong, I think that's where we stand right now. It's working great. Our experimental system that was developed on Earth with the implementation partner, which is Bioserve on this project. We have worked with NASA imaging team and we're ready, to take picture and run our experiments. So what the astronauts will do is they will push fluid into those gel-coated, mucus-lined, it's an artificial mucus for us, but in those mucus-lined tube, and then we're going to push the fluid back out of the tube and see how much fluid gets trapped, how quickly the fluids can be pushed back, depending on the amount of mucus lining that we're using. So those are the experiments that are going to be conducted on board the ISS, and then we'll be kind of on standby here and looking forward to analyzing those data and making sense of them. So to conclude, really excited to have this opportunity to work in a zero gravity environment, to work with the implementation partner, Bioserve, work with CASIS and NASA and the astronauts to carry this project forward, and then build fundamental knowledge and hope to develop therapy to make treatment more efficient for patients with, respiratory distress syndrome. And I was going to insist on the fact that this would be really an improvement for adults because the treatment works well for infants. All right, that's what we're hoping to do.
Fantastic. And once again, I would encourage media, if you do have questions, please raise your hand. If not, I do have a couple of quick follow-ups on my end.
Great.
So, I had the chance to join your team a couple of weeks back to shoot a video on this investigation. And again, I was really captivated on how fluids or, a transport investigation could also have profound impacts on life science research or future therapeutics for patients on Earth. Can you talk about how projects like this blend both engineering and science? You kind of touched on it a little bit, but maybe, dig a little deeper in.
Right. So I think no matter how good the drugs, are, if they don't make it to the region of the lungs where they're needed, then you don't achieve, the goal that you're trying to achieve, and you don't make the patient feel better. So our approach is very much build on fundamental knowledge, develop your understanding of the fluid mechanics, and then you can develop the therapeutic side, right? So one of the things we're trying to understand is, do you get better drug delivery if you use larger plugs or if you use a series of small plugs, right? And then there's going to be also the question of how are those drugs modifying how the plug is being transported. What you've got to understand when you're thinking about the transport of a plug of liquid is either the plug of liquid is transported as a block, at a certain velocity down into the respiratory system, first driven by gravity and then driven by capillary effects, right? So either it's moving as a plug and then you're delivering as much as you injected, or you're having some sort of destabilization of the plug. And so you could think that you could think of two effects. You could think of the formation of a film behind the plug that is then going to coat regions of your respiratory system where you don't need those drugs to be delivered, right? They could even get stuck in the mucus and never make it into the region that is important for breathing, or that has been affected by the infection. So that's the first problem. And then in addition to forming this film, you could also have droplets that get deposited behind. And so those are the kind of things that you don't want when you're thinking about therapeutic effects. From a fluid perspective, it's fascinating to think about how the presence of mucus and this really sticky gel, as you've seen during your visit, can modify how the fluid flow is happening. In the lab, we're actually using a model mucus because it's a lot easier to handle, and it's easier to control, right? We can control the properties much more easily than we would with mucus. And the other advantage of the type of artificial mucus we use is that it's oil-based. So it's not going to dry as it's waiting, in Florida to be loaded and then make its way onto the ISS. So that's the reason why we use a model system and try and get a better understanding, so then other researchers can pick that up and develop therapy.
Fantastic. You just answered my next question that was going to be,
Sorry.
Are we sending actual mucus up there, or are we sending kind of a substitute thereof? And maybe just kind of outline why we're sending a substitute as opposed to actual mucus, and then we'll go from there.
Right. So you've had a chance, and I don't think you've tested it, but I think we had my student put his finger into a container filled with this artificial mucus, and the response of this material is very similar to what you may have experienced with putty. And it's in the sense that you get this elastic response. It wants to bounce back, but if you pull on it gently, it's actually flowing. So that's what we call a viscoelastic material. And in that sense, the fact that it's kind of somewhat fluid, somewhat solid, in that sense, it mimics the mucus in our respiratory system. The mucus in our respiratory system is really, it's a complicated fluid, and it's a fluid whose properties change a lot depending on how you feel. I mean, you know that from, having a common cold, right? So we've all experienced the complex rheology and of mucus. And so what we wanted to do was really simplify things and gain a better control over that rheology, or that mechanical response of the gel. So we're using a silicone-based gel. The two really kind of practical advantages of a silicone-based gel is that it's inert, right? So we're not exposing the astronaut to anything that would be toxic or unsafe on board the ISS. And then it's a gel that doesn't dry, right? Maybe I should not reveal this, but I made a sample before a break, and so I decided to take that sample home, which was supposed to be, I don't know, a long weekend maybe. And then the sample got stuck at home, and it was there for 6 months. And when we pulled the sample out, we realized it was extremely stable. So an accident became a good way to to decide that this was the perfect system to send on board the ISS.
As Bob Ross said, happy accident, right?
That's right. That's right.
Great.
Tested in the California sun.
No, awesome. Well, thank you so much, Dr. Desser. Greatly appreciate it. And from now, we're gonna segue over to Dr. Ken Saban, who is the chief scientist for Redwire Space. Ken, it seems like every launch, your team is flying new facilities to support R&D on station. Can you talk a little more about the upcoming pillbox and the research that your team is doing to support its capabilities?
Thanks, Patrick, or should I say Captain?
You can call me Captain, yes.
So Pillbox is the flagship project for our up-and-coming Pillbox series. We have a number of versions of these. Our Pillbox unit is essentially a laboratory in a box. We have a facility on station called ADSEP, and the Pillbox plugs in, and you can see it there. The one that we're flying on this flight is a Pillbox FC. It's a fluidics cassette, as you see there. It's a number of bags and tubes and pumps, and it's a little laboratory. You plug it into the ADSEP system. It has power and data connections in the back, and it initiates a process of pumping fluid from bags into and through the pumps into the other bags. And we can do different things like run chemical transformations or grow crystals or study different proteins, peptides, and look at their degradation. And this is what the device was built for. And with our partner, Eli Lilly and Company, we're running a couple of different experiments to start to explore the scope and limitations of this type of approach and this specific technology.
Fantastic. Thanks, Ken. And, a quick follow-up on my end. So this is not Eli Lilly's first trip to the space station. Can you maybe talk about some of the things that they have done previously and, how this relationship evolved?
So as it turns out, in my previous career, I was an employee at Eli Lilly and Company, and I was called by people at CASIS, at the people who operate the International Space Station, U.S. National Lab, Patrick and Mike among them. And I was asked would I like to run experiments in space. And we used it at Eli Lilly and Company as an opportunity to investigate interesting science and do things with NASA and with the National Lab, but also explore our own innovation and look for opportunities to do new and fantastic things. We ended up running 5 separate experiments in that during my career at Lilly. Everything from looking at investigational drugs that were being prepared to potentially go to market, looking at how materials dissolve when they float on the ground, but in space, that doesn't have the same meaning. So how do they dissolve when they are a jumble and not just floating on the surface? We also looked at crystal growing, a couple of experiments at crystal growing, and we ran an experiment to study lyophilization. That's freeze drying of material. As it turns out, when you go to freeze dry bulk material on terrestrially on the ground, it oftentimes will layer out. It looks like a cake where some of the layers are powder and some are crystalline. And we wanted to understand, is that an effect of when you freeze it, it's frozen in water, or is it when you dry it, it goes directly from the solid phase to the gas phase? And to understand that, if we could understand that, we might be able to adjust our program on the ground to make up for the fact that we oftentimes don't want them to separate out like that. So those are the experiments we ran in the past. And Lilly is people, after my time are carrying the flag forward for Eli Lilly and Company. It turns out that this flight with investigators from Lilly is not the only set of experiments being run as this part of the mission. There's actually other experiments that are run on next missions as well, some with Lilly and some with not.
Fantastic. It's great to see that Eli Lilly is going back to space and doing it with your team. And then I see that we do have a hand raised from Will Robinson Smith.
Hey, good afternoon, Pat and Ken. Hope you're both doing well. With Spaceflight Now, Will Robinson Smith here. Good to see you both. Question to you, Ken, about this pillbox. Once it's on station, will it require any interaction with any of the crew on orbit, or once it's plugged in and set up, does it just kind of run on its own and do its own thing? Thanks.
That's actually a great question. So the pillbox system, these cassettes, they do require some astronaut intervention. So the astronauts, once the cargo vessel makes it to station and docks, the astronauts will pull the payloads out. Other materials are in there with it. But when they pull our system out, it will be unpackaged and it will have to be plugged into the unit. Although in the future, we are looking at robotic systems that will be able to be automated on some potentially uncrewed vessel. For now, we're sticking with crew doing the loading of the system, making sure the facility is operating as it's supposed to, and then it sort of runs autonomously. And when it's done, the crew member will pull the cassette out, repackage it, and then put it back into a capsule for to be deorbited. Now, in this particular mission, this effort was funded through the In-Space Production Applications Program through NASA, and part of the requirement that was set up, sort of an agreement between Redwire and NASA, was that we would attempt to do something a little special with this mission. And what we're going to do is have the astronauts, once the set of experiments are done, pull the cassette out, open the box, and pull the tubes. They have little quick connects. They can be pulled out safely, and then new experiments put into the box. It can be closed back up and then reinserted and run again. So we're going to in this particular mission, attempt what we call a fluid transfer, or a fluid switch, a fluid cassette switch. So in general, though, the boxes are made to be run autonomously and sealed so that the astronauts don't have a lot of interaction. But if necessary, we're going to show that astronauts can even open the box, switch out, do other experiments with them, and ultimately make them even more versatile.
Awesome. Great question. Thank you very much for the answer. And then also on top of that too, Ken, your team, obviously we're launching Pillbox on this investigation, but I think that your team is also supporting additional bioprinting in space. Can you provide a little more insight into some of the recent highlights in this area and what is next?
So over the now a couple of years, we've had an ongoing program to build and deploy a bioprinter. So this is a device that, like a printer like you'd have at home, prints out onto a surface. And in this case, it prints in 3 dimensions. So it will print a layer and then print a layer on top of that. And it can do so with what we call bioinks. These are materials that are made of cells and other materials that make up what we believe is a very close likeness to human tissue or other tissue. And on a previous mission, we flew the facility, the large device that does this, and a cassette. And the cassette was set up to print out a meniscus. And we successfully printed the meniscus on the last flight and returned it. And it has been returned to our partner, Uniformed Services University, for study. And it was kind of a demonstration that the concept and the hardware worked. And now on this flight, we're going to be flying a new cassette. This cassette will be to print heart tissue. And this is not thin. We're considering this what we call thick heart tissue, which could ultimately lead us to printing not only heart patches, so kind of tissue therapy, but even doing whole hearts. I mean, that's ultimately the long-term goal of this type of effort, is to print organs for transplant, and even organs for transplant that may be derived from your own cells. So they would be genetically identical, and that eliminates a lot of the issues associated with rejection. That's a long-term goal. Ultimately, that is what we want to try to get to. But in the short term, there are other applications of this type of technology. The production of tissue, human tissue, and maybe even genetically identical tissue to a potential patient allows us to study pharmaceuticals or other therapies with that tissue as a surrogate, not only for the person, so you don't have to test it on them, but right now the pharmaceutical industry is really dependent upon using animals for testing or other in vitro or in vivo models. And being able to test something on your own tissue would be extremely helpful, not only from the standpoint of better modeling towards you or the person who's going to be the recipient, but also in eliminating the ethical challenges of using animals. And in this type of system, you may even get much better statistics, since the tissue we create each time could be made to be nearly identical in each little batch or each little well. So there's a lot of opportunities there. And our biofabrication facility, our BFF facility, is really a big push for the organization from the time I've joined the company, and I know it will be on into the future.
Awesome. Thanks, Ken. A lot of great stuff from your team, and continued success on this mission and beyond. All right, we're going to move along now. So this mission has multiple investigations on it that are looking at microbes. So joining us today from Boeing, and actually all the way around the world in Australia, is David Corporal, a research engineer who will highlight the Boeing antimicrobial coating investigation. David?
Thank you, Patrick, or should I say Captain? Before I get into the specifics of my payload today, I want to provide a brief overview of the context within which this payload sits. So I'm sure, as many of you know, Boeing has been in human spaceflight for decades, all the way from the Apollo program to programs such as the ISS and the CST-100 Starliner. Additionally, my division within Boeing, Boeing Research and Technology Australia, has collaborated heavily with Boeing Houston on their human spaceflight work. Boeing Research and Technology Australia effectively acts as an internal research division, touching on all aspects of the company, from commercial to defense to space. This specific collaboration with Boeing Houston has spanned areas such as astronaut health, investigating antimicrobial technology, wastewater management, human factors, as well as input to the Starliner program, covering design, human factors, and even astronaut training. And so with this, I'm proud here to be on the webinar today to talk a little bit about our antimicrobial technology efforts in space. So microbes are the germs all around us, which include bacteria like E. coli, fungi such as black mold, and viruses like COVID-19. Historically, these microbes have posed a risk to crew health, spacecraft systems, and interplanetary contamination. And despite technological advances, they still pose a risk today. Studies have shown that in space, some microbes grow faster, they mutate more rapidly, and they have an increased antibiotic resistance. At the same time, the stresses from space travel cause immunosuppression in astronauts, which make them more susceptible to infections. Further, case studies from past and present space stations, Mir and ISS, show that microbial growth can negatively affect spacecraft systems. Lastly, there's a risk of forward contamination when undertaking interplanetary missions. You don't want to go to Mars only to find out that a microbe such as E. coli thrives in that environment. So, given these reasons, microbial control needs to be considered both in low Earth orbit and beyond, where physical mission support becomes either much harder or practically impossible. And it is in this light that Boeing is collaborating with researchers at the University of Queensland to develop an antimicrobial surface coating for application to both spacecraft and aircraft. This coating is a polymer which has broad antibacterial and antiviral properties. It's fast-acting, durable over a long period, and has a degree of self-cleaning. The principal investigators of this technology and of this payload are Dr. Jason Armstrong of Boeing and Professor Michael Montero of the Australian Institute for Biotechnology and Nanotechnology, which is the research institute within the university that we collaborate with. I'd like to acknowledge the potential of this polymer to mitigate disease transmission within aircraft, but that's all that I can say about that for now, because I don't have enough time to speak on that point further. We've previously flown a payload with this polymer in 2020 to 2021. That was a simple tech demonstrator to show antimicrobial efficacy in space. Building upon that, this payload, ISS antimicrobial coating or Boeing antimicrobial coating, aims to further characterize how the polymer performs in space by investigating its efficacy against aerosol deposited microbes, touch deposited microbes, and the coating's durability after crew interaction. This is going to be done using 6 sets of hardware placed in 4 different locations on station, where we would expect high concentrations of microbes. These hardware sets are made up of multiple samples of 5 different materials, and these materials are representative of high-touch surfaces from which you would expect microbial transmission between people to happen. Some samples are coated with the polymer, while some are not and will act as controls. The astronauts will touch the touch efficacy and durability samples 3 times a week, while the aerosol efficacy samples won't have any interaction. The experiment is scheduled to run on station from November to April next year. Just before return, the astronauts will swab the surface of the samples, and those swabs will be returned to Earth for analysis in a lab down here. Project closeout is expected around mid-2024, and we'll have completed, both the lab and the data analysis. In terms of the hopeful outcomes from this project, we have 3 broad outcomes that we're expecting. First, there will be microbial growth on the control surfaces. And then second, in comparison, there'll be minimal to no microbial growth on the polymer-coated surfaces. And third and finally, there'll be minimal to no coating coverage loss, which matches the past durability results that we have from labs on Earth. In terms of the benefits from this research, they can apply to both Earth and space. On Earth, the results from these experiments act as a further vote of confidence for the application of this technology to aircraft, airports, and other areas where mitigating disease transmission is a priority. And then in space, this technology could help mitigate the issues mentioned before of astronaut health, spacecraft systems, and interplanetary contamination. And in doing so, it would assist in making long-duration crewed spaceflight to the Moon and Mars more viable. And that's my payload in a nutshell. Thank you.
That's a great overview. Thank you so much. Quick question on my end. Is there a reason for why you selected the mission duration or the length of this in the manner that you did?
Yeah, so it's striking a balance here with an eye to the long-term space flight aspect here, as well as long-term application on Earth. You want a testing environment that has that longevity there, because one of the benefits of this particular technology is that it is a persistent disinfectant. It keeps a surface clean for a lot longer than just, say, bleach. You could think of cleaning products in terms of the two axes, one of how effective it is and one of how long it how long it takes to act and how long it lasts. By having this mission over the period from November through to April, we strike that balance between getting exposure to microbes over a long period of time whilst not being up there too long that it will take a while to get results.
Perfect. And then are there any other industries that, that this type of R&D might be applicable towards in the future, depending upon, some of the results that are generated?
Oh, absolutely. So being an aircraft manufacturer, a main focus is, say, aircraft, but then also spacecraft, that I've mentioned before at the top in terms of where a lot of our work has been. But also, as I touched on briefly, there's the application to anywhere where mitigation of disease transmission would be of importance. So there's the potential for this to be applied to areas such as public health, public transit, and food preparation environments, where you really want to ensure that you aren't transmitting potentially pathogenic microbes there.
Perfect. Yeah, I was wondering if there might have been some potential translations towards like healthcare and whatnot. So you kind of answered the question from my end. Fantastic. Well, David, thank you so much. I think I speak for Dr. Roberts on our end, where he is a major fan of all things microbes. So again, looking forward to seeing how this investigation plays out for your team, and hopefully there'll be future ones that we can collaborate on too.
Oh, thank you, Patrick.
And our last speaker for today's webinar is going to be Dr. Catherine Gardner-Vandy. She is an assistant professor of aviation and space at Oklahoma State University, and she will be discussing an education outreach project titled Choctaw Heirloom Seeds.
Halito, Captain, that's hello in Choctaw, and Yakoki, which is thank you for having me here today. I am visiting with you all from Oklahoma, a state that has 39 different tribal nations. And like in the introduction, as a citizen of Choctaw Nation and as an assistant professor at OSU, I'm really excited to represent our Choctaw Heirloom Seeds project today, in part as a co-PI with the other co-PI counterpart, Dr. Ian Thompson from Choctaw Nation. And we do this project with Choctaw Nation, with Oklahoma State, with the NASA Science Activation Program, with Boeing, and with Oklahoma State. So we really, really appreciate being here today. So I'll describe a little bit about our project. Through this project, we're sending about 16 ounces or a little less than 500 grams of 5 different types of Choctaw Nation's heirloom seeds up to the ISS. Our seeds will stay on board the ISS for on the order of months to experience the conditions of space, to experience radiation and microgravity. They will get taken out at some point to be handled by an astronaut to take some videos and some pictures. But basically, they will be in storage most of the time so that they can have those experiences of just being on the space station and getting irradiated. After a few months, they will come back to Oklahoma, and students at Choctaw Nation's boarding school called Jones Academy will plant the seeds alongside seeds that were not sent to space. So the students will be able to do some investigations about those 2 different types of plants and see what observations they can make about differences in their growth between those that went to space and those that did not go to space. The entire story of these seeds' journey will be documented after the fact into curriculum for middle school grades as part of OSU's NASA Science Activation Program called Native Earth, Native Sky. Within that Native Earth, Native Sky program, we build Earth Sky STEM curriculum with different nations within Oklahoma to hopefully show the Native students who are doing the curriculum, but also show everyone that Native culture and Native traditions can be beautifully braided together with the Earth and the space sciences. So our goal in the very long term is to see more Native American students taking part in STEM fields and have those numbers of Native American bachelor's degrees and then master's and PhDs grow into different Earth and space science STEM fields.
That was a great overview. A couple quick questions on my end.
Sure.
Why those seeds? There's 5 that are going up, but what was the determining factor for those respective seeds?
Yeah, so the 5 different types of seeds, we've got Choctaw sweet potato squash, we've got corn, a type of corn that would be used very traditionally within Choctaw Nation. We have a couple different kinds of peas, and then we have a leafy green called lamb's quarter that will be going. And those are all very traditional Choctaw foods. These seeds are 5 of, I believe it's 6 or 7 different types of seeds that are available to Choctaw citizens as part of the Growing Hope program. This is a program that banks all of these heirloom seeds, and citizens can request the seeds to have their own gardens. And the goal there is to really have the dissemination of the seeds, and for Choctaw citizens have very healthy Choctaw traditional foods. So those 5 particular seeds are very important types of foods within Choctaw culture.
Awesome. Thank you for the background on that. And then you also mentioned too that they will be on station for a couple of months. So that means to me that it's probably not coming back down on SpaceX CRS-29, but rather staying for a little bit while longer.
Yes, yeah, we're not exactly sure when the seeds will be coming down, but we would like them to be on station for long enough that they really do have that experience of being in microgravity, being irradiated for a certain amount of time, so that when the students do plant the seeds, they might be able to see some differences that can be observed.
Are the students planning on putting like a hypothesis of what they think is going to happen with the seeds in space versus those that are compared to the ones that are being grown here on Earth?
Yes, we hope to do a lot of pre-work with the students to talk about the seeds journey. We will talk about what rocketry means. How does spaceflight even work? We'll also ask the students a lot of questions about what they think spaceflight might do to seeds like this, so that when they make those observations, they can come back around and see which ones were correct and which ones they may have to rethink.
Well, great program, and again, thank you so much for communicating. What to expect with this. So, awesome. Well, I want to say thank you very much to all of our panelists today. I also want to thank the media that were able to join and listen in the public who are watching via the live stream on YouTube right now. So as of right now, we are still slated for launch no earlier than Sunday, November 5th at 10:01 p.m. Eastern Time. And I encourage everyone to look on our launch page for videos and stories on some of the investigations that were discussed today, as well as other investigations that will be participated on, again, during the duration of this mission. For real-time updates, I encourage you to visit nasa.gov for additional information on launch itself. And again, looking forward to a great launch. Thank you again for joining us. Live long and prosper.